Yo, what's up now? It's AstroSQL Codes here, back with another video, and today we are going to be talking about the abstract data type of stack. And stack is fairly similar to an array, except it follows the criteria of philo and LIFO. Philo being first in, last out, and LIFO being last in, first out, and that you can only access items from the top of the stack, nothing else. Think of it kind of like a stack of books or a stack of bricks. A better example is a stack of bricks. You really wouldn't want to take something out from the middle of the stack, else everything would just like fall over. Well, this is a very similar scenario, and we're going to be looking at two types of stacks. We're going to be looking at a stack based off of arrays and a stack based off of a linked list. And let's get right into this. So as you can see here, we have our public class array stack, and it implements the stack interface. And the stack interface here is just a classic interface with all the correct methods that we need to have the correct stack. And so as you can see here, we have type T as an array, as a instance variable, and just the total size. So in the constructor, we set the size equal to 0 and cast a new object as type T of the array. So obviously some pretty simple getters. We're just going to return the size, and for empty we're just going to return if the size is equal to 0, then obviously it's empty because there's going to be no size to the stack or nothing inside of it. So here we created our stack underflow exception, and this is the peak. So basically the peak isn't exactly the pop, and there are a little two different methods. So the peak is when you want to look at the top item of the stack, and the pop is when you want to take off the top item of the stack. So we're not looking at the top item, we're not removing the top item, we're looking at the top item. I apologize for that. And so we're checking to see if the size is 0, because what are you going to be looking at if the size is 0? That would throw an exception. So we throw a stack underflow exception. So we can go to the class stack underflow, and we can just see that it calls it to the exception super. Pretty simple. And then else it just returns stack at size -1. So if we're looking at a stack with a size of 3, then it's going to return the item at index 2. And we can see that stack is comprised of just one single array. And here is the pop method that I was just talking about. This also can throw a stack underflow exception, and it is the similar if size is 0, because you're not going to be removing anything if the size is 0. That really doesn't make any sense. That would just throw an exception. So that is the underflow that we have created. Basically just the opposite of a stack overflow. So we have an object, and it is set as stack equals stack at size -1, and stack at size -1 is set to null. Size is decremented by 1, and it returns the object. So what this does is it creates a new object at the last index of the array, sets that exact index to nothing, and then returns that object. So here we're looking at the push method, and this is the exact opposite of the pop method, and it's basically just like an add or any add or append to a list. It's fairly simple, and what you're looking at right now is it takes in a parameter of t and t item, so you can have any type you'd like. And so the stack at the new size, or at size, so basically if the size is 3, that means you're going to be setting the new index of 3 to this item. You increment size by 1 and then return the item. And now here we have the clear method, also fairly simple. We have stack equals just a completely new array of new objects, and we cast it into type T, whatever was declared, and we just set the size equal to 0. And here is the search method. This is where it starts getting just a bit complicated. So when you search for an object in a stack, you're not looking to search how far away it is from the bottom, but how far away it is from the top. So if you're thinking about a stack of bricks, you're thinking I have a stack of 5 bricks, and I want to grab the second brick from the top, that's going to return the value of 2. It's not going to return the value of 4, for example, because it's the fourth brick. It's going to return a value of 2 because that fifth brick at the top is declared as index 1, and then every one after it below it is incremented by 1. So we're going to loop through the array, and we're just going to see if the stack is equal to if the index is equal to the object that was passed through. And if it is, then we return the total size by the index or at, and that will get you the how far away you are from the top. And if that does not work, then we are just going to return -1. And just this simple toString was for testing. I mean, it just prints out every single item in the stack, nothing fairly special. And let's go on to the linked stack. So a linked list is similar to just a normal array or an array list, except for the fact that it has its big O notation, has many factors that are taken into account that the array or the array list aren't very good at. For example, like size, the array creates a large amount of space when you're making it, but the linked list does not. But however, an array is very efficient at finding items while the linked list is not. So what this linked list does is it has this item and it links it to another item, which links to another item, which links to another item. And these items are all pointing at spots in memory which hold different items. So we can see in the node class, we can have type T of a link, and when we set the link, it finds a new spot in memory, and when it gets that memory, it sets it to a new link. So we have this link equals the link that was passed through, and if you want to get the link, you can return the link. And this info and that info is just the info that is passed through, the information is type T. So not a little bit complex and somewhat hard to understand, but just to think about it, it's you have, for example, you would have two boxes, and box A is pointing to box B, and the pointer is A's pointer is pointing to memory in some random memory that holds box B's information, and that's how this works. Oops. And so now we can see the linked stack right here. We have public class linked stack of type T implements that stack interface just to make sure we have all the correct methods. So we have private int size, and we have a node of called stack. And what these nodes are just different spots in memory that the previous node is looking at. So we can create and remove and destroy nodes, however many we'd like. So let's get started. We're going to set the size equal to 0. Same thing with the size. If we want to get the size, we just return it. If we want to check if it's empty, we just say if size is 0, then we return that. So now, same thing with the stack underflow. For the peak, we're going to throw a new exception if the size is 0, because we're going to be looking at nothing. And then here's where it starts getting a little bit complicated. So we create a new node of type T called current or cur, and it's equal to the stack that we made at the top when the object was created. So then while cur.getLink is not equal to null, cur equals cur.getLink. So basically what this is doing is this while loop is iterating through the entire stack, and while this current is pointing to something, so it's not pointing to null, it sets current equal to the next link. So it's going to move to the next spot in memory and see where that node is pointing to, and then it's going to return the info that holds at that specific link or that node. And now we have the pop, same thing. If size is 0, we throw an exception of the stack underflow, and the same thing here. Node T, LL node of type, current equals stack, and we're just going to loop through this again. So what we're going to do is we're going to get the link.getLink this time, because we want to look 2 in advance to make sure that we're not going too far. And while that is not equal to null, cur equals cur.getLink. So what this does is it actually stops one before the desired spot where we want to where we want to remove it or pop it. And what it does is it sets this link to null. So the link that we were supposed to stop at, it sets the next link to null. And then we have, before this, we have to find the item that we're returning. So we set type T of return equal to getLink.getInfo. And then, so it sets, like I just said, it sets the current link to null, because if we were to set the next link to null, the next link is already set to null because it is pointing at nothing. So it sets the previous one to null, and it discontinues that break in, it breaks the memory from the one that we're at to the last one in the stack, or the top stack, decrements size by 1, and returns the type T of object that we just previously created. Now here is the push. Here is the push. So we create a new node of type item, and what we do is if size is 0, then we just set the stack to the new node, and that's about it. We increment the size by 1 and then return. And then here we go again, ll node t, so of type current equals stack. So then we keep iterating through the entire linked list, and when we get to the end, when that final one hits null, we set the link to a new node and we increment size by 1. So the reason why this isn't getLink.getLink is because here we wanted to stop 1 early to cut off the connection between the last 2. However, we're trying to add 1 in this instance, so we want to reach all the way to the end and set that last link to this item that they have passed through. We increment the size by 1 and then return it. So public void clear, all that does is just removes all the items from the list, and then size is equal to 0. We reset that. And then search, here we go. So we have count is 0, and okay, this is one thing I forgot to talk about. This also returns, like the previous one I just said, this also returns the distance from the top. So what this is going to do is, while the current link is not equal to null, so while the next link has something there, while it has memory, it's pointing to a new memory, and the current link dot get info, so the next info of the link equals O. So while that is false, then we are going to set cur equal to the next link. Excuse me for my dog, I really apologize for that. Let me re-explain that real quick. So while the current node, and we get the info of the next link equals the object, we are going, while that is not true because we don't want it to run, if it equals the next object, then we set the current node equal to the next one, and we increment count by 1. We can have this counter right here, and then if size is less than 1 or size minus count is 0, then we're obviously going to return -1 because that's just going to be a false search. And then after that, we're just going to return the size minus the count, which is the total size, and minus the distance from the bottom, which will give you the distance from the top to the current where the object is. And there we just have a 2-string. And yeah, that's about it. I mean, there's not much else to it. These were just testers for class. And that's about it. So, like I said, if you have any questions, always feel free to contact me or reach out to my email. And this will always be posted on GitHub, so there's no need to worry about source code of any sorts. And I really hope you enjoyed the video, and thank you so much for watching.